Welcome back. It's been some delay. We're resuming. We do have an episode stashed as a not yet released, which is the second part of distributed task queue. We covered Kafka and Rabbit in the previous episode of these two, and part 2 is to be released. But it turned out it's easier to release this one first. Full disclosure, I was spending lots of time at work talking to people about how coroutines work, when to use them, what are actors good for, and I realized it might be a good episode for us. I wasn't entirely sure because it's not 100% system design. So I asked in our Slack, and I got like 19 to 1, like 19 to 0. One was my vote against, since I voted both for and against. So of non-my votes, there was like 19 to 0 or 18 to 0 in favor of the idea of releasing this episode. So we're doing it. I'll try to keep it short, but there are plenty of slides. So I'll kind of skim through the first parts when it has to do with CPU internals. The intention is that if you have those questions, you can always ask further in Slack and/or re-watch the recording or re-look through the slides, which of course will also be released. With no further delay, there are 3 larger parts to this episode. First, I'm going to do an intro of what's outside our control. That's primarily how the CPU works and how the OS kernels work. The CPU is clearly outside our control, unless we build for GPUs and FPGAs or quantum computers, but most of us are not there yet. The kernel, technically, we could control it in a way. In practice, we do, because when your code runs on Docker, or when you're under Docker, or when your code runs on AWS, you are not running on standard Linux kernels. You're running on modified kernels with tweaks being made by those providers specifically for better multithreading to begin with. But for most of us, pragmatically speaking, we are not making any changes to the kernel. We just use what is given to us. The second part is about how we build software, specifically when it comes to asynchronous stuff. Specifically when it comes to, I'll get to the details pretty soon, but specifically when it comes to kernel space versus user space, multi-threading techniques. That's where coroutines and fibers and green threads come into play. I really want you guys and everybody else to understand this from first principles, from the CPU design level and from the kernel design level, so that we can leverage these primitives wisely, not just, oh, I saw it on Stack Overflow, copy-pasted the code, it does the job. And for the third part, hopefully you have enough time to get there, I really want to get to actors, to the actor models, with my goal being to teach you how to, well, teach is maybe not the best word, to share my experience when it comes to how to squeeze the most performance-wise from your software, from your code. Because oftentimes, if you do want to get into high-performance modes, the issues lay not where people think they do. And it's really, to me, it proved to be very useful to learn the language, to explain people who don't really think much about the CPU, to learn the language of talking to them on the lowest level and ultimately get them excited and interested, so that they can also begin speaking at this level, not in this hipsterish language of, oh, it's supposed to be like this and not like that. Let's see if we can do it. I know it's an ambitious goal, but it's an ambitious meetup after all. The CPU conversation starts by talking about what is called the speed of light. Usually speed of light is a metaphorical term. In the context of the CPUs, it's a physical term. It's literally affecting the performance of our CPUs. The Moore's law states that the number of transistors doubles every 1.5 years. It's usually approximated to the performance of computers becoming faster, like doubling every 1.5 years. So it kind of does work in a way on a different level. When it comes to the performance of a single CPU, it stopped working a long time ago. The reason is simple. The speed of light, the physical speed of light we deal with, is limited. That's approximately how much distance can an electron cover in 1 nanosecond. And of course, it's all contained within a small chip, but there are tons of operations going on. So you can literally think what is the maximum the CPU can do in 1 nanosecond by thinking how much work is being done within this small chip. I've read about this analogy many years ago, and I think it's not talked about enough, so I'm going to bring it up here. If you mentally map 1 nanosecond to 1 human second, a lot of things make perfect sense in terms of human numbers. So you're a human. Imagine you are the CPU. I like this librarian analogy. You have a desk at a huge room, bookshelf and stuff. So when it comes to keeping a few things in mind, like simple arithmetic, you remember these things in your memory. So there's no delay, there's no latency, there's no extra cost to take in the previous computation number from your memory. Well, that's what CPU registers are. And registers are as available to the CPU as you can think of. So that's exactly what, like adding 2 registers one to another, that's what CPU clock cycle is about. That's a nanosecond scale. 1 gigahertz translates to 1 nanosecond. If you have to access some memory, the times where CPUs used to go to memory directly is long. These times are long gone. There are caches of different levels. So the closest one to you, to the CPU, is the level 1 cache, L1 cache, and it takes also about a second. So you have some sticky notes on your desk. If you need to do more computations, you can make notes to yourself, stick it to your desk. The room is limited. There's not much you can store there. But whatever is stored there is still available immediately-ish. Level 2 cache is a bit like a notepad in your drawer, in the drawer of your desk. It takes a couple seconds, I think about 7 to get there. So it's far slower in terms of relative numbers than dealing with registers, but it's still fairly fast. The bottom line, when you have to go to the main memory, it's about 90 seconds. It's about 100 seconds. So 1.5 minutes. So it literally is a lot slower to just go pick at a memory address that is not in your cache, because this cache line has to be warned. It's not so bad. The CPUs these days would do prefetching. They would predict, they can see the code, right? If they predict all the branches correctly and it's within the reach of this predictor, it would probably try to preload this page on time. But if it's an indirect access, so you don't know until it hits which memory location do you need to have cached, it's slower, far slower. And I've included also this basic synchronization line. It's about mutexes. We had some offline chats with Maxim. You're right, it's not really a properly measured number because mutex synchronization time depends a lot on how busy the mutex is. But fundamentally, the idea is that if some 2 operations have to happen strictly one after another, even on a multi-core CPU, there is some cost associated with having to tell one person, hey, wait, do the job, and then telling this person, okay, now you can resume. So the cost here is 15 seconds, 15 nanoseconds in this case, one time. So like 2 threads would need to take twice this much, from what I understand, to actually perform the synchronization correctly. There's a real life web page. I screenshotted the picture, but I have this link open in a second tab, and it's really, really good because it shows this slider. You can move it, and it shows different timings. The main message here is from about 2005 to the current time, not much has changed on the CPU level. So the improvements are in this area, which is mostly about SSD and hard disk access. If you look at this area, which is the CPU internals, in the past 15, almost 20 years, nothing has changed. Nothing has changed. If you go back, the picture is far more dramatic. The black dots begin growing like crazy. That's exactly what I mean by the Moore's law changing in capacity. It's no longer about the single CPU doing more. It's about more CPUs and cheaper synchronization. That's my CPU being slow because it's being recorded. So let me talk a bit about what's actually inside the CPU. It's going to help, and I'll kind of skim it through because I understand most people here, both online and offline, are not here for the CPU internals. The slides are shared, Slack is open, so don't be shy just in case. So that's an example of memory dump. I found the example program for an assembly for 1886, which is a CPU released almost 50 years ago. It computes the first Fibonacci numbers, like literally 0, 1, 1, 2, 3, 5, 8, 13. That's how it should be. I have the assembly code here, which honestly we don't need to read through. And I've took 10 minutes to convert it into modern JavaScript, just to show you guys what the CPU instructions looked like 50 years ago. Spoiler, they didn't change much up to today. It's literally one line here is literally one CPU instruction of the processor that was top-notch 45 years ago. As you can see, you can only access RAM as an array of memory using certain register, in this case SI, as the index, and there are simple increments. The only construct I have here is the while loop. In CPU is going to be a label here, like the address recorded at compilation time. And then this closing bracket would be go back to here if the decremented CX variable register is not 0 yet. So it's actually not rocket science. Even if you don't like assembly, there's nothing fundamentally difficult in understanding it. So this first part focuses on two concepts. One concept is what is called the program counter. It's effectively when you have this code, much like on the previous slide, when you debug it, you would go step by step. Well, the CPU internally does go step by step. It executes stuff step by step, and it needs to know at which part of the program it currently stands. And this is called the program counter, short for PC. If you only have the program counter, you can't really call functions yet, but you can already do a lot. You can, in fact, simulate function calls, but you don't want to, because the complementary part of the program counter is the stack. Calling a function and then returning from a function is the CPU level primitive. I'm not old enough to confidently tell you if it emerged right away in the first CPUs or maybe in some further versions, but I can guarantee you that 8086 had it, because it's just so much easier to write software using the CPU supported stack pointer. And then later on you get to interrupts. I'll talk about them in a moment. And once you have interrupts, you have to have physical stack in the CPU, otherwise it doesn't know where to return back to your user code from an interrupt. So the bottom line, you would have this idea of a stack, which is just a last in, first out data structure maintained by the CPU. So when you call a function, it puts a return address on the stack, moves the stack pointer by one or by the address, by the number of bytes it takes for the address, and executes this other code. And then when you do return, it's an assembly instruction for the CPU. It pops it from the stack, pops the address from the stack, and goes back to where the function was called from. I mentally draw it up because when I was in high school, I wrote a C compiler for an AVR processor, microcontroller to be precise. And in AVR, it's a very clean, clever idea. It's a small RISC controller. They have a clean idea that stack goes down from the end of the memory, and the heap goes up from the beginning. So in my head, it's the easiest visualization. Memory addresses 0, 1, 2 are your heap, whereas memory addresses last available byte, previous sliced would be your stack. But in most CPUs, I think stack does go down, not up. Yeah. The point here is that this combination of program counter and stack, it's a superpower. I know it sounds trivial and simple, but trust me, back then it was not. It's a huge leap from a bunch of transistors and then from memory chips to the actual general purpose computation device, which is what modern CPUs are. So if you go back in time and have to reinvent this thing, eventually you will reinvent the combination of program counter and stack. If you don't, you're doing something wrong. Or we, the human kind, are doing everything wrong. But that's unlikely. At least when you start building computers from transistors, that's highly unlikely you would come up with anything more clever than this. Some people say it's discovered and invented. I like this term. It's like the wheel. The wheel is not engineered. The wheel is discovered. It's too fundamental to our nature's laws, much like the steam engine is engineered. The wheel is not. In practice, once you have the stack, a couple more things happen on the stack, most notably local variables. So ideally, a function would use registers, and that's it. And if you call another function, you would store registers on stack, and then once it returns, so when your function is called, you would store the registers you use on the stack to preserve their values before the call, and then you would pop them from the stack to restore those old values, so that the function that called you can safely assume you didn't change the values of those registers. I think there are different calling conventions in different object linkage techniques. So I think some registers are allowed to be dirty these days. I'm no expert, but I do know for a fact that you do use the stack to save registers. And then if you need more local variables in your function, then you have registers available. You would have local variables, which would also put on stack. Makes perfect sense. Stack is already there. It's in the cache line, so it's a lot faster. All good. And of course, when you're debugging stuff, we all know the concept of stack trace. The website is called Stack Overflow for a reason. So if something goes wrong in your code, you will look at the stack trace, because that's what's available to you immediately. When you know something failed, you can go through the stack and you would know exactly where it was called from, and you can go back and back and back all the way to the original entry point for your application, function, or whatnot. I don't think it's difficult. I just have to go through it because I feel it's important as a refresher to go deeper. What I will not go into is this part, but I have to mention first of all that you have interrupts. Interrupts are like hardware level functions. Timer event is the easiest example. When you write in software for an old style CPU and you set a timer, you don't just wait for a certain number of instructions until you believe the time has come to do something else. You actually tell the CPU, hey, I want this function of mine to be called every however many seconds or milliseconds. And the timer event happens in a way that it interrupts your code, unless you're in an uninterruptible state. It interrupts your code. It puts everything on the stack, so everything including the system registers, which you assume will not be dirtied, but the timer interrupt can dirty them. And then it does this job and returns back to your function. So it kind of interrupts your function, but it tries to make sure you don't notice that. Another thing we should mention is DMA, direct memory access. You don't really copy stuff byte by byte using CPU. Most device drivers, even back then, could write to memory directly and only notify you, hey, I read this however many kilobytes from the network card. Go take it from here. For us, what's important is atomic instructions and protection rings. Atomics have to do with memory. I'll get to them soon. Protection rings, well, we're talking about the CPU, so we need to talk about the kernel. And eventually you will invent the kernel. And what makes kernels possible is that CPUs have the means for some program, some application, to declare itself superior to others with respect to access permissions. So back in the MS-DOS days, all programs are in the same space. My program can look into your program, see what it does, freeze it, change your memory, whatnot, and then return back. Viruses were crazy, Trojans and all that stuff were crazy, and security was non-existent. So CPU manufacturers invented this idea that you can have a protected mode, and then the protected mode code runs less privileged applications that cannot see each other's memory, that cannot interface unless allowed explicitly from both sides, etc., etc. That's called the protection mode, and it's done with protection rings, and that's where kernels emerged. So far, I haven't mentioned anything about multi-core CPUs. It's just a single CPU, and yet, surprisingly, here's this email. I'll keep it here for a couple moments. Most of you either know what it is right away, or there's no need to read it right now. You can watch the slides later. This is the email that Linus Torvalds wrote when he started working on Linux. Before it was called Linux, he wanted to call it Freaks. The interesting piece here is that back in 1999, it had a multi-threaded file system. Back in 1999, there were no multi-core CPUs. So multi-threading was there. What I'm getting at is that you can build multi-threaded applications on a single core CPU. That's what the kernel does. It's one of the jobs of the kernel. We would disagree what the kernel's main job is. Doesn't really matter for now. But I know for a fact thread management is difficult, despite what Linus likes to object to. So there were multiple schedulers on Linux. Eventually, we have this CFS right now, I think. Doesn't matter for our purposes. My main point is that when your code runs multiple threads, the CPU doesn't know what a thread is. The CPU just runs instructions. And you can do multi-threading on a single core CPU. The kernel would do its magic so that your threads don't collide with one another. And on multi-core CPUs, well, your threads would run different CPUs. They could even be reassigned across CPUs. In fact, oftentimes they do. You have to do extra work to force them to be stuck to one core, and I don't think that is guaranteed by most modern OSs. There's physical reasons why it's important to be done. Surprisingly, when you overuse one CPU, it heats, it warms up, and it destroys the CPU if one core heats more than the others, literally. So you have to, first of all, you cannot overheat it, so you have to clock it down. It literally runs on lower clock rate, so it's slower. And then if it overheats a lot, it physically deforms the chip. So most operating systems would actually shuffle your tasks, your threads across CPUs to make sure the CPU is warmed up evenly. Crazy stuff, right? And now I know I'm going really fast, which is good. But I think from what I said so far, we know enough to build a version 0.01 kernel for an operating system. So literally, my favorite trick is to say, imagine you have nothing, and you have to reinvent this from scratch. That's my way of learning from first principles. That's how I interview people. That's how I coach people sometimes. So I don't think it's feasible to assume we go back 20 years and build Linux kernels from scratch. But technically, we have enough covered by now to understand how this would work. And we will build a multi-threaded kernel because we're going to use system interrupts. So your system interrupt, your kernel just wakes up a certain number of times per second. There's a magic constant called HZ for Hertz. I'm not positive it still exists in the kernel, but I know it was there for a long time in Linux kernels. The kernel just wakes up however many times per second and does its magic with deciding which thread should execute next. It could be a system thread, such as managing file systems or device drivers, or it could be the user thread, of which there are plenty. That's what the scheduler does. It decides who executes when and in which order. Another fun fact, the first multi-threaded CPU kernels used to take up more than 5% of CPU utilization for these tasks. So you could literally have your code run more than 5% faster by not writing software that runs on a kernel, but writing the kernel that runs your software. This trend is slowly reversing. It's called unikernels. You can write your own code that is a kernel itself. I wouldn't recommend it for most tasks, and the overhead these days is under 1%. But just do keep in mind that kernel overhead is real. And what is important here is what is called preemption. I think it's pronounced preemption, but I'm not sure. The way it works is clearly most people in the early days of software used to write their software as if it's the only thing that executes on the CPU. So from the product market fit perspective, if you want to build a multi-threaded kernel, you would need to be able to execute those applications in parallel. You cannot expect them to cooperate. And if you want to run two things in parallel, your kernel has to support running two things, each of which believes it's the only one running. This is called preemptive multithreading. So you preempt some other tasks from executing. You slow them down. The way it actually works is the kernel distributes CPU time in what is called quants. So between quants, within each quant, one thread is running. Then the CPU wakes up by the timer event or by some other uninterruptible thing. It doesn't matter for now. I'm no expert. But the CPU wakes up and its scheduler decides which user thread should the next quant be given to. So you can easily imagine you have two threads, two processes, and the CPU just gives each of them every other quant, 50-50 split. In fact, the scheduler can do a lot more, because many times these applications, this user code, would maybe read from a file or read from network, in which case there's no need to wake them up early. All they do is waiting for new data. So the kernel can be slightly more clever. Oh, this process is waiting on the pending I/O task, and I/O is controlled. I/O is input output. I/O is controlled by me, the kernel. So I know exactly when to wake this thread up. because I know exactly what should happen for this thread to stop waiting. That's what the scheduler does. So I mentioned what is called preemptive multithreading. There is this other concept called cooperative multithreading, and it's a very clever idea. In fact, we're slowly getting to what this episode is about. Cooperative stands for user-level tasks cooperating. Cooperating means they would give way to one another. I've done my job, it's time for you to do your job, and I expect you to give control back to me so that I can continue doing my job. In a perfectly cooperative multithreading world, what happens is the best practice, the being a good Samaritan in cooperative multithreading is kind of simple. You write your software so that you do small things of work at a time, small chunks of work at a time. Once one chunk is done, the next chunk is waiting on something external. From network, from disk, from other processes, other small workers. So you do your small work, you assume you are interrupted for the duration of this small amount of work. And then you give control to the scheduler, be it the user, be it the OS kernel or something else, we'll get there. You give control away, and you expect to have the control back once this thing you're waiting for is yours. That's cooperative multithreading. Interestingly, and it was a surprise to me when I was preparing these slides, Windows 3.21x used cooperative multithreading for real. So there were attempts back then to build operating systems based on cooperative multithreading. Somehow they didn't fly. So today we have this weird mix. If you're familiar with how browsers work with modern JavaScript, web workers in JavaScript effectively are a clever mix of cooperative and preemptive. I'll get there too. This is important to cover, because what makes fibers and coroutines so powerful is that they actually take us back to these cooperative times. On the one hand, our OS kernels are by design preemptive. On the other hand, a lot of things can be done better if you don't involve the kernel at all. That's the gist of this talk. We'll get there soon. Before I close on part one, once we have multi-core CPUs, multiple cores have to synchronize with one another. On a single core, you can just say I have critical sections. I have some piece of my code that cannot be interrupted, like ever. But in practice, it would only guard it from interrupts. There's not like system level interrupts, not other processes, because the other processes in a properly implemented preemptive multi-threaded environment, they would know you exist. They just don't know of your presence. At some point, you start writing multi-threaded applications. At some point, you want things to run in parallel. You want, within your own application, a couple of things are happening concurrently, and you want to leverage that. And then concurrency becomes an issue. What if your different parts of your code access the same data structure? And we get to all sorts of craziness. You have like read-write mutexes, you have log-free data structures that are optimized for these use cases. But fundamentally, at some point, you need to synchronize. Think of any simple data structure operation, such as adding to the queue. When you add something to the queue, there are operations that happen one after another. You take the current queue head pointer, for example. You increment it by one, and you copy the contents of the next element into this memory location. If you're interrupted in between these two operations, there would be more than two, but it doesn't matter. If you're interrupted in between, the reader of this memory would read an inconsistent state. Synchronization primitives are exactly about this, making sure that different parts of code can concurrently access the same data structure, and they would at least see it in a consistent state, in a logically consistent state. That's where we get to mutexes, that's where we get to synchronization. I really don't want to get into the details. Just keep in mind that there are two things to worry about. One is atomics. It's a relatively new concept. It didn't exist 50 years ago. It's the idea that concurrency can be guaranteed not only on the CPU level, but also on the level of connection between the CPU and the RAM module. On your motherboard, you have the CPU and you have memory slots. These memory slots have evolved over time. These DIMM modules have a special interface that is not just give me the contents of memory from this location, from this block, send it to my CPU cache. It's not the only thing they do. There actually is a physical system call on a hardware level where the CPU tells the memory, I want to access this location, and by the way, block it from other CPUs as well. So if someone else wants to try to access this location, stop them, tell them it's unavailable, have them try again. That's how that's how atomics work on the lowest possible level, and that's why they're faster than mutexes, because mutexes require all the CPU threads to stop talking to the memory, because you don't really know what can be changed by other processes. It's not rocket science, but it's hard, so I will not go there. Just keep in mind that atomic variables can be leveraged from user space. It's what your code can do if you use atomic CPU instructions. Your software, when you say it's atomic, your compiler would know it has to compile into atomic CPU instructions. Atomic CPU instructions execute on atomic CPU core without the OS kernel having to know anything about synchronization. Whereas mutexes are inherently kernel space objects. You have to make a kernel call, which is slow. Slow as in extra, I think 150 cycles over that. In the modern Linux, we don't have mutexes, we have futexes, which stands for fast user space mutexes. It's a very clever idea that combines user space locking, atomic space user space locking, and kernel level locking. So basically, when you don't need the kernel will not interfere. But in most practical, but if there is contention, if tasks do wait for one another, it will still go to the kernel level. So the OS scheduler, the kernel scheduler, would know which task is waiting for what. I'll get there eventually. Just keep in mind there are two things. There are a lot more on the kernel for synchronization. I don't know much of it, and I'm no expert. Just the TLDR is atomics are CPU level and memory level, physical level access. Mutexes are originated kernel space. Futexes are kernel plus user space, slightly faster in the case of no contention. This was part one. The biggest point here is that I want you guys to have this understanding of the demarcation line between the CPU and the kernel. And the biggest part is that the kernel doesn't know about threads at all. Threads, I apologize, the CPU doesn't know about threads. Threads as a concept are introduced by the kernel. All of us use threads as if they are CPU native primitives. It's okay, that's what they are supposed to look like for us in most high-level programming languages. But ultimately, at the CPU instructions level, there's no such thing as a thread. The CPU just executes code, instruction after instruction after instruction. The kernel that runs in ring 0, in protected mode, is what makes it possible for multiple processes to work concurrently without knowing other processes exist. Moreover, not just threads are a kernel concept. Synchronization primitives such as mutexes are also a kernel concept. The CPU doesn't know something is a mutex, and it doesn't have to. It's slightly different with futexes because they use atomic assembly instructions. But when it comes to mutexes that have to wait for something in the kernel space, such as the input-output operation result, if multiple threads are listening on a port for a socket to connect, for an external party to connect, they are waiting on a kernel primitive, and the kernel would decide which thread to wake up once the connection is established through the network, which the kernel would know from the device driver. So it's an example of a kernel scheduler doing the job of waking up the right thread. The CPU has nothing to do with it. The CPU just executes the code, which in our case is a mixture of kernel plus user. Hope it was not too fast. I enjoyed it. Part 2. Ultimately, we wanted to get to user space threads, user space primitives, user space ways to run things faster. The concept that is heard a lot, that is used a lot these days, is green threads. And a lot of people just say, oh, use green threads. Well, what are green threads? They will tell you, well, it's threads, but they're not kernel level threads, so they're faster and you can have more of them. Well, that's true. First of all, in most kernels these days, when you start a thread, the kernel would allocate tons of memory, specifically for the cache. I think the default is 10 megs for Linux. So 10 megs means that if you have a gig of free RAM, you can only start 100 threads. And not all RAM is free because the kernel uses something. So even on a 32 gigs machine, the highest number of threads you can run concurrently, if you allocate 10 megs per thread, would be 3200, right? So 3K. At the same time, you can easily hold 1 million open sockets on the same Linux, on one Linux box. So clearly there's no single CPU thread per socket, which makes perfect sense. You don't need 10 megs cache for something as trivial as receive something from the socket and respond with yes. So there must be some magic that allows for this to happen that is not necessarily in the OS kernel threads, which is how green threads come into play. And we get back to cooperative multithreading. In fact, so the gist of how green threads work is a combination of two simple ideas: back to cooperation from preemptiveness and being stackless. It's a hard topic. I'll do my best to cover it in simple terms. So, first of all, let's tackle cooperativeness. If you want to write the code that would handle, so again, simple examples are best to explain. So let's take, as a hypothetical example, let's take the task of writing a piece of software that opens 1 million network connections that are simple A plus B tasks. You receive 2 bytes and you return A plus B. If you're more of a modern backend developer, imagine you receive a JSON of two numeric fields A and B. You compute A plus B, you respond with the JSON. Don't facepalm. JSONs are actually not that slow. They are slow when you have to unescape strings. If it's just about 2 numbers, that's not too slow. It's like under 10 times slower, and a factor of 10 is not large. It's you can live with it really. So you want to build a service that can hold 1 million concurrent connections. Over each connection, you can receive an A plus B request, and you respond with the sum. Well, obviously, the CPU can clearly perform more than 1 million additions per second. Even if you factor in all this network overhead, so you need to talk to the device driver, you need to extract data from it. But even if you factor all this in, if it's a single socket that sends you data, packet after packet after packet, and you respond packet after packet after packet, you can do many millions per second. But with 1 million concurrent connections, it's a lot harder because you need to know what to execute next. If the number is not 1 million, but maybe 100, and if you use CPU or if you use kernel threads, what would happen behind the scenes is you would use the kernel scheduler. Each thread would be responsible for its own connection. Each thread makes a block and call. Read the next 2 bytes. Read the next A plus B. And then the thread enters the wait mode, and the kernel resumes this thread once those 2 bytes are received. That makes perfect sense as long as you have enough threads in your kernel. As we talked before, you cannot have 1 million threads, so you would have to do something on your own. What it would be is that this queue of what to be executed next, this point of decision, oh, I have this data coming in from the network, it has to go to this thread, or this thread emulation, this green thread. This logic would have to partially be in the user space, because the kernel can only hold so many threads, far less than 1 million. So this has to do with concurrency. If you have multiple, clearly you have a small number of kernel threads. You have a small number of CPUs, let's say 32, but you have a lot of work to be done. So what happens is, within one execution thread, it can be a thread of the kernel in the thread pool of your executor, or it can be just one CPU per se. Within one executor thread, your code will have to cooperate. If your code runs for too long, or refuses to return, or just does while true do nothing, unless some preemption takes place, you would just block the whole thing, or at least this CPU, or this kernel executor thread. So cooperation means there's an implicit contract, implicit agreement, that your code does not run for too long. It waits for an external event, such as the data coming over the network. You respond to it, and you yield control. You tell others, hey, I'm done. You can do your work. And then it's back to the scheduler, which is the kernel scheduler in terms of kernel threads, or the user space scheduler in terms of green threads. That's it for cooperativeness. For the stacklessness, it becomes the computer science exercise, because what coroutines effectively are, there's a term that helps explain what they are. The term is resumable functions. The function can be suspended while it waits for something, and then resumed at this particular point. Now you need to know exactly where to resume. if where is just the surprise program counter. Here's your code. This instruction is where to resume from. You just store the pointer. That's simple. If it's potentially a recursive tree of functions, you need to maintain the whole stack of them in software, because it's no longer the CPU stack if you have to be concurrent and yield to one another. So it can all be done. It's not too hard, and the good thing is it is done by frameworks and by languages for us. Many languages these days, I know for a fact Go and Kotlin are famous for this, but many languages these days take this painful part away from us, but I think it's useful to understand how it works behind the scenes. If you have an asynchronous function, a resumable function, that is run in this coroutine green thread environment, if it calls other asynchronous functions and they yield from inside, you have a huge call stack that you yield from, and then you need to get back to this huge call stack. So it has to be reconstructed artificially. It's not a CPU stack. The CPU stack is one per thread in the kernel thread. Hope it was not too tricky. So when it comes to cooperativeness, what you end up with is what is called the finite state machine, FSM. It's possible to write a finite state machine manually with your own hands, and I'll show you in a few slides. But effectively, what happens in most modern programming languages or frameworks is the framework does this transpilation, if you wish, for you. So the whole idea of good frameworks for asynchronous programming with coroutines is that you write on a high level for other humans to read. And what the CPU sees is totally different from what you wrote. So you have A followed by B followed by C. It translates to do A yield. Hopefully something comes back to me. The control comes back to me after A is done, and I do B because I know A is done, and then C. That's why they're called stackless, because presumably there's no call stack. Example is the best, and I wrote one. So here's a piece of code that I actually wrote recently. It's almost production, no kidding. The only thing I've done, I've renamed this Postgres connection. This term doesn't exist in Node.js. It's called, I think, pg.pool or something. So it's supposed to be a super simple example. It's a Node.js, it's an Express.js. You have an HTTP endpoint that is called db_date. Once this endpoint is hit, your function is called. The first argument is unused, it's request. The second argument is the HTTP, which you use to send the response. The function is called, you open a connection to Postgres, you run a query, the SQL query, which is just select current date. Once the query completes, the other function is called. Now for this exercise, I first terminate the database connection. In real life, I would not do it. In real life, I would first respond. But for the exercise, let's say I first make sure the connection to the database is closed, and then I send the request. So this is a modern JavaScript syntax. In ES5, which I don't like, but sometimes use for illustrative purposes, these are functions. Like this is called error notation from ES6. So these are functions. And we can see there are three functions defined here: the Express.js HTTP handler, SQL query runner, and connection closure. I realized later on that this is a bit of a cheat because Postgres connection is not created instantly. I think the way it works internally is it just creates a JavaScript object, and the actual connection happens in the call to query. I don't know for real. Don't quote me on this. In the real life, this Postgres connection could also be an asynchronous function, but let's skip this for now. We have two to work with. We're not gonna make this one asynchronous because it's called multiple times, but we can make this function asynchronous and this one asynchronous. Here's how. Here's the modern JavaScript async syntax, async await. It exists in many languages for many years. You define an async function, and then you say, here's my database result, which is awaiting for the result of this call. And then I await for the Postgres connection to close, and only then I send the response. So far, it should be trivial, I assume. What it actually translates to internally is something like this. Let's not go into these details, how to wrap the magic function into an async function, but you do have a simple function that receives as this arguments the index of its current stage and some context that is shared between stages. At the first stage, index 0, you parse the arguments, you start the connection, and you run the query. And you don't wait, you just return. You return to the framework, and the framework decides what to do next. And the ultimate callback from this Postgres query would not call your function, it would call the framework. The framework would eventually proxy this response to your function. It could be later if it's busy, it could be in a different CPU thread, but you don't care. All you care is, I've done my quick part here, and for the slow part, I yield back to the framework. That's what yield effectively would do. Then you have the second stage, index 1, where you collect the response, save it in your context, and you have another synchronous request, which is ending the connection. And then at the final stage, when the connection is successfully ended, you send the response and you're done. This is how it looks like when you translate an async await flow into a finite state machine. So you can see this has 3 states, 0, 1, and 2. I call them stages, but they technically are states. The topology of these states might be different. It might be more difficult. If you're waiting for multiple things, if you have like 2 awaits, then there's no reason to believe these 2 awaits would be completed in the same order. If like await A, await B, it's not that when you're done waiting for A, then you start waiting for B. B can be done before A. All this is factored into this translation job of the compiler and/or the framework. You just write your linear human code in the yield fashion, in the async fashion, so that the framework can do whatever it has to do while there is available CPU cycles. Not too hard, right? Moving on. So yeah, this is how finite state machines would look like. This function will be called multiple times. That's why it's a resumable function. That's the essence of cooperative multithreading. Now the important thing, I kind of mentioned this, you can run a million functions like this concurrently. So that's one of my favorite examples. That's what many people these days don't get. So let's go through it closely. Imagine you actually run this code against a real database, but your real database can handle a million or more concurrent requests per second. Each request takes a while to process, let's say a second, but it can handle a million requests. That's actually quite easy to assume these days, because if it's hard for you to imagine the single database object on your local host, on your physical machine, that can handle a million calls per second but returns within a second, not immediately, think of it as a cloud database. Think of it as a database that has 10,000 nodes, and each node can handle 100 requests per second. But because of network round trips and load balancing and stuff, the call actually takes 1 second somehow. So I wouldn't say it's a real life example, but it's closely resembling some real life use cases. The point is, if you write synchronous code, if you use kernel threads, there's only so many threads you can use. Let's say you use 1,000 CPU threads, 1,000 kernel threads on your, 8-core or 32-core machine. All these threads will be waiting for the response from the database. So even though the database can handle millions of operations per second, because each operation takes a full second to respond, most of the time you're busy waiting for those responses because you have so few threads. You have so much fewer threads than the amount of work you could do. If you look at the CPU utilization, if you open top on Linux or Task Manager in Windows, you would see that even though you're using many threads, the CPU is almost idle. There's nothing happening because you really need this much CPU work, and all the time you do, all that you really do is you're waiting for the kernel to tell you, oh yeah, I got a result for you via the network. You can do your next stage. So that's exactly the use case where user space threads, where green threads or coroutines would be super helpful. I'm not saying it's a real life example, but seriously, it's one of the best illustration of the use case where you just cannot rely on kernel threads. Period. It's impossible for the kernel. I mean, there are tricks. You can have kernel threads use smaller stacks. There's a concept apparently of I forgot the term, segregated stack, segmented stack. There's a segmented stack. So on the kernel level, it can say, oh, I'm going to allocate you a small stack. That if you run out of the stack space, I'm going to give you another small array, and I'm going to pretend it's a continuous memory space, even though it's not. All those tricky details. In practice, for this exercise, what you want to use is coroutines and green threads, user space scheduling. And now we talked about cooperation. I do want to talk about the stackless part. I feel it's a bit too advanced though. So the point is, if you debug your asynchronous code, from a few slides above, when I used async await as stages, if you debug this code, you have a breakpoint, and your code hits this breakpoint. As a developer, you would of course see the previous steps. You would see that the part above your breakpoint was executed, the part below it is still to be run. You could probably inspect variables, watch the variables in this scope. But it's so far from what the CPU actually sees, because on the CPU level, on the kernel thread level too, when your function is resumed at a certain stage in the middle, it's not called by the previous stage, it's called by the framework. And a lot of things could have happened within the framework between these two calls. So in practice, what would happen is your call stack on the kernel, on the CPU level, would not contain the previous stages of your function. It would just contain a few higher level steps of the framework calling your code into the right place with the right arguments. That's why if you want to maintain a lot more data in the stack, you'd have to, well, first of all, you cannot use a stack. You cannot use the CPU stack at all, because the green thread executor may even want to run your code on a different CPU core to begin with, on a different CPU core or on a different kernel level thread. So your stack is expensive to travel back and forth. What you would do instead, you would use the heap. You would allocate something on the in this variable I called context. So you would populate your context and then only use the variables you have in the context. Whatever you declare as a variable in an async function doesn't make it to the CPU stack. It makes it to the context, and then you can extract it back from the context. And the framework would have to carry this context everywhere when your function is not done, when it still has to be resumed when something happens. Yeah, that's really the biggest message here. Don't try to use stacks aggressively when you're writing resumable functions. Even if all the state machine construction is handled by your framework or by your language, just keep in mind that because it can be resumed far later in a different kernel thread on a different CPU, you better allocate your variables in the context. In fact, most languages wouldn't even let you know this. Like in JavaScript, any variable you declare would be in the context, because JavaScript has its own memory model, its own garbage collection. It's a longer conversation how this works. I do want to emphasize that if you want to have an asynchronous function and do lots of algorithmic recursive calls, traversing like a directory tree or something, you probably don't want to do it asynchronously. You probably don't want to do it in the proper like recursion-based fashion. Rewrite your code to be iterative, not recursive, or be prepared for disasters. Or just run this part of code in a preemptive multithreading fashion, so that it pretends it has exclusive access to the CPU, does this slow operation, and then sets some mutex or pushes something to the log-free queue. Hey, I'm done. This other thread, the green thread, the coroutine, can wake up and consume the result of this computation. I know I'm going fast, but I hope it's good fast. What are the downsides of this style of programming? Yeah, what I just covered. The state must be self-contained in the context. Don't implement state machines manually. It's error-prone, and your coworkers would hate you. It's really hard to read such code. It's really hard to extend it. It's really easy to make a mistake. That's why I think, it's my hypothesis, I'm not going to claim it's true, but I think the widespread popularity of green threads and async await is one of the reasons why managed languages are still so popular. It's because once you switch from kernel threads plus preemptive multithreading into user space stackless cooperative multithreading, the lifetime management of object becomes so much more difficult. In the good old days of single-threaded preemptive multithreading, you just use a stack. Whatever your local function needs is put on the stack. The stack is guaranteed to be preserved until whatever you call returns. So your memory model is simple, especially if you speak not even C++, but C. Whatever you allocate on the stack is on the stack. If you call something, it's yours. If you pass it by the pointer, until whatever you called has returned back, this pointer is valid. When you return the top-level function, the pointer is no longer valid because the stack will be overridden by something else. Well, that's exactly what does not work with coroutines, because there's no stack to begin with. It would have to be in a dynamic memory, it would have to be in the heap. Somebody eventually would have to clean this up. That's my guess is that this is exactly the reason, well, this is one of the reasons why garbage collection and why managed languages are still so widespread, because it's really hard to think about this manually. In a way, Rust is exactly designed to take care of this problem. We'll see what happens. I'm not going to make predictions here, but it's a noble goal. I endorse it, I support it. It's just really hard to do it automagically. And many people don't really realize how difficult it is behind the scenes to manage memory when you start mixing different styles and accessing different objects, different variables from different places that are a mixture of synchronous and green thread-ish. Well, finally, we're going to get to fibers and green threads. So I found it easy to start this story from coroutines just because they emerge organically and natively from the conversation. In practice, it might even be easier if you're telling the story to a friend to start from fibers. But in our case, well, I chose the other path. So coroutines are just single functions. They can be resumed, they are transpiled, compiled, built, packaged into finite state machines. They are stackless, they are cooperative, and that's what they are. Coroutines don't need to know of one another. Coroutines are they're all equivalent, essentially, to the framework. And there's no reason you could call a coroutine and leave it hanging. Like detach a coroutine. Let's say it runs forever. It's just pointless. It makes no sense. Fibers or green threads are the opposite. They try to emulate kernel threads as closely as possible. So you can start something asynchronous, and it's going to be a fiber. And it can run its own thing. It can wait until the next frame and do its own thing for the next frame and run forever until you stop it. Fibers can join one another. That's another threading term. I wouldn't say much here, except it has to be said that if you have one of them, you can easily emulate the other. Once you have coroutines, you can emulate fibers like this. Once you have fibers, coroutines are natively emergent there. They're just two different names. I hope the way I told this story, I hope makes it easy to understand the concepts bottom up, so then you would not get confused. So yeah, they are both stackless. They are both cooperative, not preemptive, and the way they are run by the kernel is, in practice, what almost always happens is you have a thread pool to run certain block of coroutines and fibers. You could do it on a single CPU core, which is often beneficial because you can do it on a single kernel thread, which is likely a single CPU core, but as we spoke of, not always. It could be beneficial to run all your coroutines and green threads within a single kernel thread for cache locality reasons. The cache is far more likely to be warmed up if your coroutine knows it's going to wake up in the same kernel thread. Modern schedulers of coroutines, I believe, even if you use a thread pool, they would try to schedule the continuation of your coroutine on the same kernel thread for cache locality reasons. Or you could configure it if you want, because in most cases you would be glad to trade sub-millisecond delay to being on the same core. You want to utilize the CPU effectively 100% every single core, so you don't want to wait for cache synchronizations, but that's rocket science. In practice, just keep in mind that in most cases, in most modern frameworks and languages, there is going to be a thread pool of one or more kernel threads that manages your coroutines and fibers, and that's normal and healthy. That's how we all do it. And yeah, the biggest, I think I mentioned this before, but it's a good time to refresh. Going from user space to the kernel space and back is slow. It's another 150-ish CPU cycles, just because of the protection rings magic. It has to, like, your sandboxed secure code that cannot affect other processes talks to the kernel, and the call has to cross the boundary. It's because the kernel can do anything on the system. That's why user space schedulers are just faster, especially if you have millions and billions of green threads, millions of concurrent coroutines. You save a lot of cycles, a lot of CPU cycles by just not having to cross this boundary. This is not applicable when you are waiting on I/O operations, input-output, file system, network, or whatnot. But if all you're doing is a bunch of CPU level operations, let's say, so the way I talk about this all the time, it's going to be down there in the slides too. If you want to optimize your software to highest possible performance, you really don't want to be mixing I/O and compute in the same threads. You would have like one or few CPU threads reading from your network, and they would put stuff in bulks, not byte by byte, maybe like megabyte by megabyte, into a log-free queue. And this log-free queue is in memory. And now your user threads can just wait until there's data in this queue and start their own work. So in practice, the part that reads from network in, let's say, 0.5 megabyte blocks and populates this log-free queue, this part runs in one of the kernel threads. You don't care about this. This thread would not be expensive because large block reads are cheap. It's all DMA based. So in practice, even if your code is eventually I/O bound, in practice, most of the CPU cores will be busy running your own custom software code. You will probably have this weird fan out of the execution tasks to be done from the same external request. But you don't need to wait for each external request on the I/O. You receive a megabyte of data which contains multiple requests. It's pre-packed for you, pre-packaged for you. It could be by another service, like a gateway. It could be by another kernel thread of your application. But you would just separate I/O and compute, and the goal for you is to maximize the throughput of your compute. The goal for you is to 100% load every single CPU core that is allocated to your compute, to the compute part of your application. So there you don't have I/O blockers. There you don't need to go to the kernel level scheduler, because everything is happening within your own coroutines and green threads. And I think it's important to stress that we covered the above. Hopefully it was easy to follow. We covered it from first principles. Literally, if you go back in time today, when none of this is understood by the humankind, I bet you would invent the same ideas. I bet you would suffer through every single step. You would invent the program counter, you would invent the stack, you would invent synchronous functions, you would invent protected mode. First you would invent system level interrupts, IRQs, including the timer interrupt. You would invent critical sections, like block interrupts while I'm doing this, so that I'm not interrupted. You would invent preemptive multithreading, because that's how you would learn how to run multiple processes concurrently. You will build protected mode, ring 0 versus ring 3, so that those concurrently running applications don't affect each other. And eventually you would realize, oh, yeah, I need a scheduler, because I have multiple threads waiting on the same object, and this scheduler might have its own priority queues internally on the kernel level to wake up tasks in the right order. You would struggle with that, and then you would realize that your users are too comfortable, too used to writing synchronous code, A after B after A, C after B. So you'd rather support the syntax, and you would invent async await, and then async await would actually compile back inside into these state machines, which I showed you about how it works. I'm not saying any of this is anyhow legacy. I don't like all these parts, and maybe eventually we're going to do it better with like CPU level support for cooperativeness, for example, or better mixture of the two. But I do believe that if you follow my story closely, all of this makes sense step after step. There's no way around each of these individual steps. Add to this that CPUs are also evolving, reacting to the demand of what the software needs. So, for example, atomic operations, compare and swap, stuff like that. They emerged specifically because we needed to build faster software, and kernels were not fast enough at switches. So it's a pile that everything affects everything, but eventually we are where we are, and it's not too bad. I mean, I started this talk by showing you that for the past 15-ish years, not much has improved in performance. on the lowest level of the core. So we seem to have reached what could have possibly been reached technologically. We seem to be living in the world where the next advances will be in the software space. And that's what I'm trying to articulate here, how the next advances in the software space is exactly what we're living through right now. Part 2 recap. If you can afford for your code to be fast and cooperative, if you don't need the stack, and if you don't need to wait on network or file system, on I/O, you probably should use Firebase and Coroutines. If you need the stack, if you rely on preemption, that's how you write your software. And if your code is I/O first, well, you probably want kernel to be widely involved. In practice, you can actually combine the approaches in a pretty clever way, like I tried to describe above. You can have a single kernel thread to read from the network, fill in some log-free queue or whatnot, and then have your own kernel thread pool of the remaining cores, running your coroutines effectively to do all these compute tasks. You probably have one kernel thread for the queue of the incoming data on your socket, and another kernel thread for the log-free queue for the outgoing data of the same socket. You could have 2n of those for n sockets, making this up, but I know for a fact that's how it's designed in high-frequency trading, so that you bind a few kernel threads or even a few CPUs to do these tasks in a blocking fashion, but in larger blocks, and like in a buffered way in terms of network and disk. And then you dedicate the rest of your CPUs to quickly do your own compute, which can be 100% green thread coroutines based. Part 3. What have we learned? How can it help us? I hope it was interesting, but I don't think it answers many practical questions. What's in it for me? How do I use this to build better software? Well, I think the practical question that always starts this conversation is, why is my code so slow? What's wrong? I wrote perfect code, but it's somehow 2 orders of magnitude slower than I expected it to be. What am I doing wrong? Look, I'm using the language correctly. I'm using all the correct functions. What am I missing? So let's take a look at the modern simple service in a modern day company. That's kind of my real life example, to be honest. That's what I struggled with the team I'm working with. I had a hard time explaining how coroutines and fibers could help and why certain ideas are just not good enough conceptually. But in order to explain this, I had to pretty much do half of the homework. Well, third of the homework I've done for this talk. So that's what I'm sharing with you. So imagine a simple real service in a modern day company. It accepts external requests, most likely HTTP or gRPC. It has some internal data structures, like a local cache. When it has to respond to an external request, it's a mixture of two. It has to manipulate its own internal data structures, and it has to make external calls and wait for those responses. So it could have to talk to maybe 2, 3, 4 other services. It may have to go to the database or 2 different databases. It's not uncommon these days that you would have to go to a SQL database and to a Redis, and then maybe back to SQL because something in Redis gives you another foreign key to look up. So this is your business logic effectively. And eventually, once all this work is done, you can compose the response, JSON, gRPC, or whatnot, and send this response back to the caller. Sounds simple. Here's my approach to performance, top down. Let's say we're doing all this. Like, ask yourselves, what throughput does each step have individually on a single CPU core? I'm not saying it's the best question to ask yourself. It's the way I think about it. So I need to get requests through network. Well, there is no reason I cannot receive data from the network at more than 1 gigabyte per second. So if my input request is 100 bytes, that translates to 10 billion per second easily. Add to this the overhead of parsing the message. I guess gRPC is faster. I know it's faster, but it's not super fast, by the way. The protocol of gRPC and the protobufs are not really designed for high performance parsing, but it doesn't really matter. It's fast enough. JSONs are slower, but still, I cannot possibly imagine this being too slow. It will certainly be in the tens of thousands of requests per second. Now you have your internal data structures, hash maps, dictionaries, one to n, n to 1, n to m maintainers. Well, yes, cache locality is big. If you need to update multiple of those, it could take a couple iterations, but still, I cannot possibly imagine the well-designed application where a single external call would need to do so much with internal data structures that it cannot run at 100k operations per second. If you design your data structures correctly and just forget all the network, forget all the I/O, just have this function that maintains your internal data structures, have the in-memory prepared set of operations to execute, and just have a for loop that calls this function. It's hard to imagine a real-life application where this function cannot run more than 100k times per second. In fact, millions is a more reasonable estimate, I think. Now, composing the response back, those JSONs or gRPC, and sending those back is also gigabytes per second. So it looks like each individual step should be super quick, but somehow the ultimate throughput is far slower. You could correctly say, wait, I'm talking to a database, and I need to wait for the response, so that's why my time is spent. Well, yes, but you don't have to load the CPU 100% while this time is being spent. We covered this before. If you use coroutines properly, if you use green threads, you always have your CPUs 100% busy. Every single CPU core will be 100% busy, not waiting for those responses, but composing the next requests, parsing the next responses, and doing its own business logic. So still, to me, it doesn't look right that the performance of the system is below, let's say, 50k QPS. It really doesn't. I'm not saying every single system like this must be super fast. It's probably like I would prefer it to be the case. I would prefer us to live in a world where frameworks are good enough, so that the default assumption would be, I have a simple server. It can handle 50k QPS or 100k QPS. We live in the real world of business where there are trade-offs. So sometimes 1.5k is good enough for the service, and you need a few boxes for redundancy anyways, and you don't need to scale anything, and the language you use is far from fast, so just live with that. I understand and appreciate this approach. Nothing wrong with it, but still, to me, it's a challenge. How come it's so slow? And eventually, you do hit the bottleneck, so you'd rather know what to do. You'd rather be in position to tell your teammates quickly, oh, if you want to optimize this, if that's the bottleneck, let's look here, here, and here. We're going to do it right now. So I'm going to skip this slide. So imagine you can make your CPUs all busy. Why is the QPS so slow? Well, there are a few reasons, a few possible reasons. One is you have some algorithm that is not optimal. That happens. You have some order n squared, where it should be order n log n, or even you have something single pass not done in single pass. If that's the case, you can find it and you can fix it. In fact, one of the best ways to figure out what the slowest part is very simple. You just have your code, you have the synthetic test, you record some traffic, you send it to your service in an isolated sandbox, you run it, and you break it. You just stop it, Control Z. And you test the debugger, and you look at where it is. If you do it 10 times or 100 times, you would find where your code is stuck most of the time. If you find it stuck in some weird container traversal, because you're looking for a single key by looking at all the keys possible, well, you know what to optimize first. There's no question. So sometimes what it's going to be the slowest, sometimes what will be the slowest part is the price we pay indirectly because we want to use easier development tools. I mean, garbage collection. Of course, your code is going to be faster if you write it in a language that is not doing garbage collection at all. But I'm not expecting all the Java code to be gone tomorrow. In fact, I fully understand why many companies decide to keep writing in Java. Well, that's life. Sometimes you would find that you're making too many kernel space calls, and the user space to kernel space is slow. Maybe if you don't do batching, if you don't do buffering, if you just write messages one by one, that's often the cause of slowness. But what you would really often find is that, getting ahead of myself. Another reason why you could be slow while the CPU is still loaded 100% is that you are abusing busy waits and spin locks. That's the second part of this slide. That's how this easiest busy wait looks like. You have some variable that is volatile or atomic or whatnot, so that this loop is not optimized away. And it's really, really on a CPU level. On every single iteration, that can happen close to a billion times per second. Okay, close to 100 something billion times per second. On every single operation, it would look at the value of this variable, check if it's true. If not, wait. It's literally the donkey from Shrek 2. Are we there yet? Are we there yet? Well, it's easy to imagine the application where you have a 32-core machine. Every single core is based 100%, because every single core is asking, are we there yet? Except for one slow task that is about to get us there, but it's been interrupted all the time. That's not impossible. And don't get me wrong, busy waits do have their place. Sometimes it's a good way to write code. In fact, Futuxes work like this. They try a few busy wait iterations, but then if they're too slow, if they realize no chance I'm going to be done quickly, no chance this resource is going to be available quickly, it switches back to Mutex and to kernel level scheduler queues. So in these two cases, the CPU is fully loaded, but you're still slow. What often happens instead is you fail to load your CPUs, and that's a problem by itself. If you see that your software can run faster than it does run right now, you look at the CPU load, top in Linux, Task Manager on Windows, and you see that you're nowhere near 100%. So your code is waiting for something. You know it can run faster, but it doesn't run faster because it's waiting. What is it waiting for? The short answer is that the CPU cores are waiting for one another. The logic that you've used to write your software, to write your code, is making the assumption that I'm done with this and I wait. And if there's one point that one piece of code that has to complete before others can resume, they're all going to be waiting for this piece of code to complete. In a way, it means that you are imperfect in breaking the whole job into smaller pieces that depend on one another in a proper way. You have this bottleneck where something has to be done before others can resume. They would love to resume. They probably have some other work to do, but they are designed, the data flow is designed in such a way that they do not resume until something else completes. That's what is called contention. That's why it's the biggest possible point of difficult debugging in speedups. So a loosely defined contention is as a state where total weight is no longer negligible compared to total work. If you look at like 100 or n100% CPU utilization, ideally you have some tiny fraction of that is spent in synchronization primitives and stuff like that, and the other n times 100% CPU resources at any given time unit, any given second, if you wish, are spent doing useful work. In a high contention environment, it's the opposite. In a high contention environment, the useful work is not being done, and the threads are waiting. The cores, the processes, the coroutines, call them however you wish. They are waiting for something beyond their control until this something is done and they can proceed. So how do you improve this? One of the first advices is figure out, aren't you locking too much for too long? So an example I always use, it's hypothetical, but it's so easy to follow, is imagine you have some counter. You have some counter of requests within your code. And for each request you handle, it's incremented by one. Well, you can say it's going to be an atomic variable, or it's going to be a mutex locked, mutex guarded variable, and you just do this variable plus plus for each request. But if your requests are super slow, super quick, you would spend a lot of, like, if your request is super slow, then I don't care. But if your request is super quick, then a non-negligible fraction of this request is doing this counter plus plus. And you can have 1,000 green threads or 1,000,000 green threads. They all do their own work, but they all have to increment the same counter. And when they start incrementing the same counter, they have to wait for one another. So the solution here is obvious. Don't increment it by 1. Increment it by 1000, or increment it 100 times per second per each green thread, or just increment counters independently in each thread, in each kernel thread. And then at the time you want to get the number, that's when you lock those counters by mutexes, and you come up with the sum, or you don't lock them, you just sum them up, and you're off by whatever small number by design. That's a simple example of a single lock contention point that you can just remove. Ironically, further ways to improve this code have to do with SysDesign principles. One is to use CRDTs, conflict resolution data types. So instead of locking the data, you can just make the change in a way that is, if multiple changes are made to the same object, they are resolved later on asynchronously by some other thread to get to the final value. So counting elements, as in the plus operation, is just one example of a CRDT. It doesn't matter in which order do you sum them up. Eventually the sum will be computed correctly. There are tons of data structures that support CRDTs, that can be supported by CRDTs. Can be tree structures, can be different containers. So if that's your contention point, you can use such a data structure and you're good to go. Log-free data structures are awesome. So queues are one of the best examples, but with multi-version concurrency control, I think that's the term, MVCC, multi-version concurrent control, I believe that's what long events do to you. The idea is that if it's like a database, it's some object, and it's affected by multiple transactions. Let's say there are 10 read transactions and 1 write transaction. You just freeze the object in memory in a certain way, so that the read transactions see it in the state it was when they started. The transactions can all run at different time frames, they can intersect with one another in different ways, but there are algorithmic means to make sure that the transaction that started at a certain time sees the same state of the object. So you can mutate it, it is changed. Once it's no longer used by any random transaction, the old copies can be discarded. It's usually done by a B-tree-like approach. So you have pointers to changed objects and you atomically swap them to the next version. But the old pointers are still letting you to traverse the original state of the data structure with no changes. Sounds advanced, I know, but the idea is that you can have a log-free data structure that you can on the one hand mutate and on the other hand not block. It's a bit slower to use in a civil peacetime when there is no contention, but this price certainly pays for itself if what you want to do is avoid contention, avoid threads waiting for one another. And yeah, the previous example with busy waiting, I know we didn't have time to cover optimistic versus pessimistic locking. The example of busy waiting before was an example of optimistic waiting, optimistic locking. Optimistic locking is when you write your synchronization code under the assumption that the resource you need is available. So 99.999 whatever percent of the time, it's available immediately or after a super short wait. That's the use case where busy waiting is okay, because you just waste a few CPU cycles here and there. If you have to wait for a second, like a network packet arriving, that's the worst place ever to use optimistic locking, because the CPU will be busy 100% waiting for that single bit to flip in memory. So pessimistic locking is effectively this idea of green threads applied on the kernel level. When you tell the kernel, the OS kernel, here's my primitive, I need to wait on it. I'm giving you control. Call me back once this is available. In fact, kernels are so smart. That's what the Linux schedulers I cited before, like order of n, order of 1, completely fair scheduler. What they do is they try to maintain their own data structures, so that if there are multiple threads waiting on the same object, there's going to be a queue of them in memory. So the kernel knows which one to call next, and then which one to call next, and it's all order of 1 operations. In the older versions of Linux kernel, they were not order of 1. You could literally slow down the system quadratically if you have n threads waiting for the same resource. And contention is pretty much always multiple threads waiting for the same resource. If you interview for high-frequency trading companies, they would sometimes, quite often actually, ask you to implement the thread pool. So the idea is that you actually have n threads, you spin up n kernel threads, and you have the means to schedule tasks and some threads would pick this task up whenever the next thread is available after its previous task. If there is tasks to be done, it grabs this task and it does it. It executes it. That's an interview question, and the answer is when the queue is full, you don't want any kernel level waiting. You just want threads to agree with each other. Oh, I'm the thread who just became available from my previous task. I'm going to grab the next task atomically so that the next task is not grabbed by multiple threads. I'm going to execute it. No need to talk to the kernel at all. It's just between you and the other threads. Use an atomic data structure with atomic pop from that queue. But then, after the higher load phase, chances are there are no tasks. Your threads are free. So your threads are idle. So what you would do is you would not use busy waiting. You would not use optimistic lock-in. Once the thread is done through its own threads and the queue is empty, chances are it's going to be empty for a while. It could literally be seconds or minutes or hours. So what you would do is you would yield to the kernel and say, hey, notify me once there is something in this queue. And there's a kernel primitive in pthreads and in C++ these days called the condition variable. And this has a special method, notify1. It's a special kernel level call that says, hey, if there are multiple threads waiting for this, waiting on this object, on this mutex, pick one of them randomly, I don't care, and unwake it up. But just one. Don't go wake up all of them. That sounds minor, but in an HFT setting, in a thread pool internal implementation, that's what the gist is. So going back to deeper into pragmatics, it's my personal advice. If I'm wrong, blame me. But I think statistically this will be right. If you have a high performance task to implement in high performance, if you are doing everything right, you will be CPU bound. Your bottleneck would be the CPU. If your cores are waiting for one another, you need to improve your code. Go ahead, fix your code, come back later. But if all goes well, if you need to write high performance code and you're not CPU bound, you're doing something wrong. Because look, there are pretty much 4 different bottleneck sources: CPU, RAM, disk, network. Disk is cheap, so is memory. So it's hard to imagine that you have to wait for that. If you're bounded by input, if you are bound by I/O, by input/output, my idea of a single thread that is doing buffered batch reads from a network, putting them in bulks into your log-free queue, so that your user space code reads from this queue. That's the working idea. You can take it one step further and say, I don't even have this thread. I'm going to move this logic of batching input requests into a separate service. So my core box that has to be super high performance just expects the requests not in this single HTTP connection JSON, but it expects these inputs from a separate service that is putting them all together and giving me a binary stream of requests, which is currently to be more than a gig per second. So, and you can do the same at the output level. So if you really want to optimize your super low level high performance thingy, like your caches, your different data structure access, different massaging of data, slices and dices, if you want to squeeze out maximum performance there, you don't want to be doing I/O in the same box, or at least in the same thread pool. And when it comes to your own code, it has to be 100% utilizing all the CPUs you give it, otherwise something's wrong with your code. So unless there's a small fine print here, unless you want to buy latency for throughput, sometimes it's really important for your code to respond a few microseconds sooner. In this case, busy waits help. In this case, it's okay for you to burn the CPU. It's okay for you to put more machines there just for this small latency bit. That's like HFT. But in practice, you almost always don't need this. If you're an enterprise developer and you're behind service meshes that route your requests with load balancing on a Kubernetes run AWS, you don't care about this extra 150 microseconds statistically, so just write good code. And yeah, so we're close to the end. That's actually, ironically, that's how I started my slides. When I realized I need to prepare the presentation, that's how I started. Here are your bottlenecks. How do you improve them? So there is one easy thing to improve: excessive memory copying. 2 medium things, both in the memory space, allocation and garbage collection, and 3 hard in compute: user space, kernel space context switches, block contention, cache and validation. For the memory, I'm not going to bother talking much about garbage collection. TLDR, don't. If that's what's your bottleneck, you rewrite your code to not do any allocation dynamically. Honestly, that's the best solution. You can pre-allocate a huge chunk of memory. You can leak memory and say, once I'm up to 90% of CPU of memory utilization, kill this node, start a new one. That's also a good approach if what you really want is optimized performance. If you leak in memory at the rate where you need to restart your code every 12 hours, that's normal. I mean, I'm not suggesting that if your code is already leaking, but if it's by design, that's okay. So really, don't get too aggressive on yourself, too harsh on yourself with memory. This can be fixed. With compute, well, it's kind of like a recap of what we talked about. Don't wait or sleep synchronously, but yield, ideally in the user space. If you, like most of us, don't work on the kernel space, just use kernel less, which means green threads remain in the user space, and that's your advice. Pragmatically speaking, if you use the kernel space threads, if you use green threads or coroutines correctly, the standard advice is to use the thread pool of n threads, where n is the number of your CPU cores. That's as long as you don't have this background CPU thread to do your I/O help. That's a standard advice. Sometimes you want to use a bit more threads in your thread pool. That's because you do have some waiting in your user space implementation. So you want to do some other work while waiting. That means you're not using your cores in the most effective way, but sometimes it's okay in practice. And of course, the biggest advice is to minimize log contention. So synchronize less, look into MVCC, CRDT, and super advanced high-level advice from HFTs, keep your cache warm. If you know you need some data from memory, you know it in advance, you need to hint the CPU, hey, warm up that cache page. How you do it? You access that memory. A common trick is, I'm not kidding, it's totally serious. A common trick is to send yourself a network message that emulates the call that would happen later. Like make a transaction for 0 cents, but they would run your code that is forced to go to that memory location. That's, if you can do it a few milliseconds before, in advance, you would literally force your CPU to preload that memory location into L2 and maybe even L1 cache, and you're good to go. I think we're close to an end. I believe it's the last or second last slide. Again, the original intent of this, I don't even know what time is it now. The original intent of this was to talk about actors and actor models. I found it really hard to explain what actors are, but after all this long intertwined intro, it should be simple. Actors are just coroutines, where you're forcing yourself to never use any other synchronization primitive but a queue. It would of course be a log-free queue. So if you need some data structure that is accessible concurrently, let's say you have a dictionary of all users in your application, what you would do is you would contain this dictionary within one actor, and you don't read this data structure. You're not allowed to, otherwise it's going to be concurrent access. You send a message to this actor, and it responds back to you with the value. So you invent CQRS within your own binary. Effectively, it becomes SysDesign in the same application, within the same executable, within the same binary. You kind of have multiple services talking to one another, and you explicitly forbid them from peeking into each other's state. One other way I like to describe this is it's the OOP done right. Like I'm one of those, I want to say few, but we're growing. I'm one of those many people who believe OOP is a terrible concept, as it was described in the past 15 years. So OOP was awesome when it just started. Objects talking to each other through messages. That's what OOP is about. Actors are OOP done right in multi-core, multi-threaded, green threadish user space scheduling world. For a long time, the term OOP was hijacked by strange people who used to think OOP is about inheritance, polymorphism, encapsulation, public protected private, and stuff like that. That's not OOP. That's what people want you to think it is. Like when I ask this question on an interview, what's OOP? I don't, but if I do, and the candidate tells me, oh, it's these 6 keywords, I usually assume they are not super senior, because these are just primitives that help you think about certain things in certain ways. Actors are OOPs done right in the modern world. So the only primitive you have is a queue, but it's super powerful. The queue gives you linearizability of requests. The queue guarantees that every single actor only executes its tasks sequentially. So there's no need to any mutexes, because every single point of data, every single data structure is owned by one actor, and every single actor is only acting on one message at a time. So that effectively each single actor has its own queue, and because each queue is lock-free, no more lock-in is needed, no more synchronization is needed. It has its own problems. Your actors could become malicious, they could not return on time. The queues could get huge because some actor is slower than expected. You could have data duplication if you have some user's hash map to handle. And this hash map becomes a contention point. All the other 50 or 100 actors have to talk to the same data structure that is within one actor. The actor first solution, like the actor pure solution, would be to have two or four of these data structures, duplicate them in memory. This duplication is the price you pay to not have to lock anything. In which case I would of course say, well, you don't have to use pure actors, right? You can have this internal service that is using this CRDT data structure. It pretends to be an actor, but it can handle concurrent requests quickly. That's, again, not rocket science, but advanced. But actors are a really good way to write code these days, mostly because actors do make people think in a paradigm that is really hard to make mistakes in. When you hire people, when you want people who are junior and mid-level to be able to extend your code without the risks of weird race conditions internally, actors are a really good bet, like company-wide. If I'm an architect for a big enterprise, I would bet strongly on actors because it makes sure, even though our code would run slower, the risk of mistakes introduced by new people who don't really understand how the code works internally, this risk is minimized. To me, it's a better end of the spectrum. The other end of the spectrum is people writing green threads manually with a huge switch statements of state machines. Like I've literally seen C++ functions that look like C functions, that a single function is 2k lines of code, which is analyzing a bunch of states, and the state itself is not just one number. It's like Cartesian product of multiple numbers. It works. It's super fast. It's impossible to maintain. So actors are the other extreme. Choose wisely, but now you know how this one works too. This must be the last slide, I believe. It's been a while. So I actually talked through it. If you have a shared dictionary, you can hide it behind an actor, and its life's going to be heaven again. And if it's still not effective enough, you can do it the old-fashioned, unheavenly way, behind a mutex or behind your own synchronization primitive. You'll be good to go. Yeah. Last slide. Takeaways. There's no magic. Nothing I've told you so far is difficult to follow, I think, or not counterintuitive. It's just, I actually hope one of the best takeaways of this event is that I believe I have a good structure in my head. I'm not saying I can convey it perfectly, but I think I have a good structure that makes it easy to think from first principles all the way down to what we have to deal with daily. So I hope that by following this structure, you would agree there's no magic. There's some legacy, but it's not like code legacy. It's architectural infrastructure legacy that is impossible to work around, because that's the history of evolution of our computation on this planet in the past 50 years. So there's no magic, but things aren't simple either. Multithreading is hard, we all know it. Green threads, coroutines, and especially actors help a lot. Knowing the first principles helps a lot. And yeah, much like we don't talk much about critical sections today. Critical sections were the primitive used for lock-in and synchronization many years ago. I think these days we should slowly phase out mutexes and other like semaphores and stuff. We should really think in terms of lock-free data structures, mostly queues. We should really think of persistent data structures that are thread safe, such as CRDT powered structures or MBCC-ish red black trees, where you can change part of the data structure, and whoever has taken the pointer to the right root of this tree has the same copy that is guaranteed to be immutable, and then once they release this pointer, it can be garbage collected in the proper way, not like Java way, but the proper queue-based garbage collection that is fast, reliable, and doesn't block you. And yeah, let's think more in actors. A lot of people think actors are the only future. I'm not an actor extremist, but I think actors are really, really good, and I'm positive that we would live in a better world if we adopt actors far broader than we have today. I'm not doing this. It's just in the slides. Thank you, guys. Do we have the energy for questions?
Dima, thanks for a great presentation. I just want to add one, like a devil's advocate for hardware threads, I mean post threads. I believe it's you can adjust the stack size which is assigned to each thread. Like in pthread, you can say that don't give each thread 2 megabytes, let's give it a little. So you can technically create a lot of threads, but it will be a pain for the kernel to schedule them.
Well, not really a pain. It's a very good point, and I would believe that kernel level schedulers are pretty good these days. So you are not likely to build a better scheduler yourself than CFSVs. It's just when you have a lot of threads with small stacks, your biggest point of pain would be context switches. Every single time your code yields, it's going to be user space to kernel space, and then back kernel space to user space. Even if you are fully stackless and you don't need more than 16 kilobytes of stack per thread, even if you can spin up a million kernel threads, I think you can. Frequent kernel to user space context switches would be the main point of contention for you, or the main point of slowness.
But imagine if there were no context switches, it's harder to manage preemptive threats than cooperating one, because like in languages like Rust, basically each future kind of pushes itself back on the queue after polled, so you don't the executor don't have to do so much work.
Yes and no. I mean, yes, but then if you use actors, or if you try to use actors, you don't access the same data from different locations, so it's logically owned by one place. And then the overhead you would pay in this case is simply the overhead of, well, preemptive multithreading, which today is under 1%. So, I mean, I agree with you that if you're trying to, even if we build a 100% cooperative multithreading application these days, unless you patch the kernel, it's still going to run in a preemptive multithreading world. So the kernel scheduler is still involved. And I've had these conversations with traders. Had this been a big issue, had this been a big deal, we would have fixed it. I just don't believe it's a big deal. You do so much more work in your green thread, in one time quant that is kernel that's given to you. You do so much work that the overhead of occasionally going to the kernel and back, occasionally being preempted by the kernel, this overhead is so low that you honestly don't bother in most practical cases. That's at least my understanding.
I have a question actually. Maybe you have any thoughts? So kind of, as far as I remember, the actors are not so widely adopted as a concept. So kind of, there is an Akka, but it's not really, it's more like a marginal, it's not like the common thing. So kind of, why is go this way? And kind of, maybe it's showing that it's not the best option for any reasons.
Good question. My guess is extremely simple. Actors came a bit too late when people already learned to think in coroutines and async await. So the value of actors is not immediate to most people these days. It's clear to me why actors are good, because they decrease the likelihood of a weird, simple, silly, multithreading concurrency error introduced by a junior developer. If you use actors, this error is impossible. If you don't, once in a while it happens, and it's a really painful one to debug. So to me, as an architect in a big company, the answer is obvious: use actors. Just because I'd rather pay not 1% but 10% overhead in CPU. I'll provision 12 machines, not 10 machines, for my service. That's the price I will gladly pay, like on the company scale. That's the price I would pay to eliminate room for possible errors. But then the response I usually get when I try to sell actors, the response I get from developers is, oh, look, Kotlin has coroutines. They're as good as actors. And they're right. Kotlin has coroutines. They are as good as actors. They don't give you thread safety for free, but they give you this illusion, they give you this impression that it's so easy to write coroutine-like code, so why do I need actors? I can't blame them. It's just actors as a paradigm came a bit too late and doesn't have good language support. That's just my intuition. I might be wrong, but it's what I struggle with when I talk about this to other people.
I'm not sure if it's actually a new idea. I think Erlang is kind of old, but it's not mainstream.
Okay, let me phrase it better. That's a good point. Thanks for catching me, by the way. I love this. When I say no good support, I don't mean there's no framework that does it or language that does it. I mean there's no good way to organically introduce actors to the way other people think. So Erlang is awesome, and quite a few big applications use Erlang. When I talk about how to build high-performance stuff in C++, it's really hard to imagine me talking about high-performance C++ for an hour and not say something like, "Oh, we're gonna reinvent Erlang here." That's impossible to not think in Erlang level primitives when you want to be high performance. But I'm not gonna make people speak Erlang. It's impossible. So what I'm trying to say is that in the languages such as Go or Kotlin, there's no simple way. Like if there was a keyword in a language, not coroutine something, but actor something, they would just give you a compilation error when you're trying to access shared state. I think it would be super widely adopted, but we're not there yet. Well, it's also the curse of this U-shaped distribution of knowledge. People who worry about this, they tend to cluster in certain companies, in certain projects that do need this knowledge, and these people know what to do. And on the other end of this distribution are the companies that don't need this. So why invest in educating people to this depth when they can still deliver and make the company profit? So an idealist engineer as I am, I would love to live in the world where we need to build high-performance software and we just slowly phase out technologies that are hard to build high-performance software in. But I'm also a realist, and we still have PHP and WordPress. And how can we talk about why actors not adopted when we still have WordPress and garbage collection that stops the world? I'm not sure if it qualifies for an answer, but it's been a while since I've been speaking for 2 hours straight, so hopefully it's okay.
That's fine. Actually, I had one more question, but maybe I forgot it a little bit, so I'll try to frame it as far as I could. So you've mentioned that all kernel calls are taking the CPU. So kind of you need to spend CPU to make the kernel calls. And the question is, why do you need to do this? Kind of for polling, for waiting the request, you need to poll like response from the kernel or for what? So kind of as far as I know, it's also kind of taking some time, and I think it can be done in async by maybe something like epoll or this logic. So kind of basically, I thought that you don't need to spend CPU cycles to wait for response from the kernel.
I'm not a kernel developer. I don't think sync async here matters.
Neither.
Yeah, I mean, I have the answer. I have the answer because I researched this when I was preparing the slides. So first of all, sync async doesn't matter here because when we are at this level of performance, Let's say you wrap all your kernel calls into async green threads. You can. It's not about how long does it take. It's about how do you squeeze the most out of your CPU. So you're still going to spend these cycles on the context switch, regardless of whether it's sync or async. So the real question is, why do we have to spend these cycles? And I agree with you. It doesn't, like, if I'm the CPU developer, I don't think it would take me more than one CPU instruction to change from protected mode to ring 3 and vice versa. You may need to save more registers because the calling convention will be different, but it's also minor. From what I understood so far, the biggest difference is memory management. I could be totally off, by the way. I didn't read through. But the thing is, in the modern CPUs, the way the modern memory paging works is there's no global address space. If you have an application, let's say you write a C code that has a single variable, and it does malloc, and it prints the address of this variable. Or if you just say int, like void main, int a, print the address of a. If you run this program 100 times, even concurrently, it's going to print the same address, even though clearly it's a different address in memory. Because memory mapping is done by the kernel. So it has to readjust internal registers to point to a different default memory, and vice versa. And this alone costs you like 50 plus CPU cycles. I might be totally off, but that's what I read. That's what is in the memory right now after what I read last week.
So basically, CPU cycles are spent not in the kind of waiting for the response from the kernel, but inside the kernel logic. Yeah, you meant that this one. Inside the and kind of context switch and inside the logic in kernel and so on. It's kind of basically what we are not controlling.
We don't control it. Yes. I wouldn't necessarily say they're spent. So I don't think they're actually spent. There's no, like, if you look at what the CPU executes instruction after instruction, it would not be 100 instructions. It would be a few instructions, but some of those are expensive because the memory mapping stuff has to be changed. That's my understanding. I think it can be loosely compared to making a jump into the piece of code that is not cached. Even though it is cached, the readjustment has to be done. Yeah, I honestly don't have a good answer. I'm no expert here. I read this a number of times. I also couldn't believe it. The famous example, if you read online, would be the get PID function. PID is PID, process ID. So presumably for each process, PID is fixed. It doesn't change during it's a Linux function. Windows has an analog. So presumably there's nothing that makes the PID change. So somehow, if I'm designing the kernel, I would plausibly ask, why not put the PID into some fixed memory address for this process? And so that get PID would not be a kernel call. It would be a single lookup. But as an example, it works perfectly because it's a super trivial operation. But this get PID takes more than 150 cycles, I think, precisely because like the work to be done is one instruction. But it has to cross the user space to kernel space barrier and then back. That's what I remember clearly after reading this stuff. The true reasons, they also wake to me.
Also, I've had the question about this kind of logic for a finished state machine. Yeah, so it's been built in runtime or it's been built in kind of in compile time. So kind of in compile time, yeah.
Of course, yeah.
And so kind of okay, so that this makes sense. But how it works for for languages like interpreted languages like Python, for example, which has pretty the same logic, or JavaScript even,
well,
which are not compiled.
If the language is interpreted, there's no compile time.
So it's been done in runtime, or kind of how it works then. We don't know when we need to know when we need to go. So kind of we need to build this context here. So basically, this context is like a huge stack, but it's not like a stack, but it's just kind of a hash map. Yes, this way, and we need to kind of to go through all these kind of states, to do all these functions, and we need to build this finished state machine in runtime, or how it works.
So it's not really a hash map; it's an array. Number of states is fixed and small. I don't think the question is that valid because even without any state machine building, you still need to parse the source code, find the closing bracket, and generate V8 code. So Even if there's no, even if we're talking like full interpretation, if you don't parse the whole source code, you just start running it like bash scripts. Even then, you need to read the whole function body, parse it, and translate it into something that can be executed. So honestly, it doesn't look hard to me. There's a tricky algorithmic part with object lifetime, but since JavaScript already is using this weird memory model where variables are there for as long as somebody is using them, it shouldn't be too hard. I've stumbled upon, I can send you a link by the way. When I was preparing the slides, I stumbled upon a C++, more like C library that built coroutines using C macros. So like yield is return some special code, and there is a framework, but the way you talk to this framework is by using macros that are just begin coroutine, yield, etc. And it actually, like on the one hand, it builds the stuff at semi-runtime, but on the other hand, it's a true green threads library that just lets you yield to other threads of yours, other green threads of yours. It doesn't sound too hard. It's actually perfectly doable.
Yeah. So basically, what came to my mind is that for each function, we need to know from which function it was called and to which functions it should go. It should go kind of for the next steps, and mostly that's it for the information. So we don't need to know the history for this function or all the previous calls.
Yeah, if it's flat, if there's no recursive calls, it's kind of simple. Yeah, honestly, if it's flat, all you need to remember is the next stage index. There's a tricky case when you await multiple things. If you await 3 things, you have to support all 8 orders in which these 3 things can complete. But that's the only tricky part. No, wait. If it's 3 awaits, you have to support all 6 orders. It's factorial, not 2 power n. I guess I am tired. All right, shall we call it? Thanks, guys. I enjoyed it so much. See you next time.